In this tutorial on industrial instrumentation, we will talk about flow measurement part 4. Here we will talk about magnetic flow meter, turbine flow meter and target flow meter. A magnetic flow meter, also known as magmeter or electromagnetic flow meter, is a transducer that measures fluid flow by the voltage induced across the liquid by its flow through a magnetic fluid. The typical landing materials are neoprene, polytetrafluoroethylene (PTFE) and polyurethane. The materials used for electrodes are stainless steel, platinum iridium alloy, titanium and tantalum. Faraday's law states that moving a conductive material at right angles through a magnetic field induces a voltage proportional to the velocity of the conducting material. The conductive material in this case of a magnetic flow meter is the conductive fluid. The fluid therefore must be electrically conductive but not magnetically. The operation of magnetic flow meter is based on Faraday's well-known law of electromagnetic induction. The voltage E induced in a conductor moving in a magnetic field at a right angle to the field is directly proportional to the number of conductors, or, as in this case, the distance between the probes l, and the intensity of the magnetic field B and the velocity of the motion of the conductor v. Thus, we get E equal to BLV of the order 10 raised to minus 8 volts. The law based on which a magnetic flow meter works is the Faraday's law that states that whenever a conductor is placed in a varying magnetic field, an electromotive force is induced given by E equal to BLV. The volumetric flow rate for a circular pipe of diameter D is given as Q equal to area into velocity. Thus we get pi d by 2 whole square into V, or pi d square V by 4. Therefore, substituting the above equation with Q, we get E equal to 4BQ by pi d, and thus the flow meter and the flow rate is given as Q equal to E pi d by 4B. The advantages that a magnetic flow meter offers are that they don't have any restriction in the path of flow. There is no pressure loss involved. There are no moving parts in this setup. They offer good resistance to erosion. They are independent of viscosity, density, pressure and turbulence. They offer good accuracy. They are capable of measuring bidirectional flow. And they offer large range of flow rates for large diameters. However, the limitations are they are expensive, they require a full pipeline, they are limited to only conductive liquids, and they are not suitable for gas and liquids which are hydrocarbon based. The next type of flow meter is the turbine flow meter. The turbine flow meter translates the mechanical action of the turbine rotating in the fluid flow around an axis into a usual readable rate of flow. The turbine wheel is set in the path of the fluid stream. The flowing fluid impinges on the turbine blades, imparting a force on the blade surface and setting the rotor in motion. When a steady rotation speed is achieved, the speed is directly proportional to the fluid velocity. The blades of a turbine flow meter are made up of ferromagnetic material. The magnetic pickup coils would be wound on a permanent magnet. The voltage pulse is obtained at the pickup output whenever a tooth passes the pickup coil, and flow is measured by counting the number of pulses. The rotational speed of the turbine is proportional to the velocity of the fluid. Thus, numerically, Q equal to Kn, where n is the number of rotation of the blade and K is the constant. Different methods are used to convey the rotational speed information. The usual method is by electrical means, where a magnetic pickup or inductive proximity switch detects the rotor blades as they turn. As each blade tip of the rotor passes the coil, it changes the flux and produces a pulse. The pulse rate is directly proportional to the flow rate. The flow range that is measured by a turbine flow meter varies between 0.5 and 150,000 gallons per minute for liquids, and for gases and air it is 5 to 100,000 gallons per minute. As the rotation of the turbine is measured by means of non-contact, no tapping points are required in the pipe. Pressure is therefore not a problem, and in fact pressure up to 9300 psi can be applied without any problem. But this of course does depend on the pipe diameter and the material of construction. Temperature limitations are only imposed by the limitation of the material of construction. To reduce losses or changes in the process temperature, turbine flow meters are available which can be subject to wide temperature variations. Turbine meters require a good laminar flow. In fact, 10 pipe diameters of straight line upstream and no less than 5 pipe diameters downstream from the meter is required. They are therefore not accurate for swirling flows. They are not recommended also for use with high viscosity fluids due to the high friction of the fluid, which causes excessive losses as the turbine becomes too much of an obstruction. The viscosity of the liquid must be known for use in this type of meters. They are also subject to erosion and damage. Each meter must be calibrated before usage. The advantages that a turbine flow meter offers are their moderate cost, easy cleaning, they are suitable for low viscosity fluids at steady moderate flow rate, and they have very good turn-down ratio. The disadvantages are, however, reliability dependent on fluid cleanliness. They are not reliable and suitable for steam flow. They are subject to wear and tear under certain conditions, and they are not applicable for viscous fluids. The next flow meter type is the target flow meter, which is also called drag force flow meter. Here, a small target or a drag element, which is of the shape of a flat disc or a sphere, is placed in the flow pipeline. The insertion of a suitable shaped body obstruction into the flow stream can serve as a flow meter. The drag force on the body becomes the measure of the flow rate. The drag force Fd exerted on the target due to the flow rate is measured and translated as flow rate, which is given as Fd equal to half CD rho g v square A. For a sufficiently high Reynolds number, the drag coefficient CD is reasonably constant. Thus, the drag force Fd is proportional to v square. The drag force of a body can be measured by attaching the drag body to a suitable force measuring device. Cantilever beam arrangement with bonded strain gauges is one such arrangement. The accuracy and repeatability produced by this target flow meter are of the order plus minus 0.5% and within 0.1% respectively. Common examples of flows measured by the target flow meter are highly viscous flows of hot asphalt, tar, oil or slurries at high pressure of the order of hundreds of bars. The advantages that a target flow meter offers are nominal initial installation cost. They offer application for a wide variety of liquids, both viscous and slurries. They are suitable for abrasive, corrosive and contaminated fluids as well. They have the measuring capability for sporadic and multidirectional flow as well. The limitation, however, is inevitable pressure drop in the measurement process. Students can refer to the following links and references for more detailed study.